In previous topics, we have seen that discontinuities constitute a weakness in the rock mass. In fact, failure of a slope, for example, is often triggered by failure of discontinuities and triggering block instability. These can occur on natural or man-made slopes. This figure illustrates two possible failure scenarios involving failure of discontinuities. On the left, failure occurs along one discontinuity whose shear strength has been exceeded. On the right, two discontinuities have failed, one in shear, one in tension. Such a mechanism has occurred on this photo. You can see that the rock is yellow or grey. Grey reflects exposition to water, while the yellow colors pertains to fresh rock that has not been exposed to water. The yellow zone outlines the volume that has fallen. The failed face are yellow, suggesting that water pressure is not the cause of instability. Instead, it is suggested that some weathering has weakened the base, resulting in a large block almost hanging from the top with some strength contribution from the back and one side. At some point, the tensile and shear strengths were exceeded and the whole block fell. Note that the back and top faces are very smooth. They correspond to existing discontinuities. In contrast, the left side is very rough, suggesting that failure did not occur along the discontinuity but through the rock mass. The issue of falling blocks can also arise underground. Consider, for example, the case of this circular excavation in a fractured rock mass having two discontinuity sets. The orientation of the discontinuities is favorable to the fall of the block highlighted in yellow. And following its fall, it is likely that the blocks around it, number 4 and 5, will also move, possibly releasing blocks 2 and 3. In some cases, the modification of the stress state plays a role in the instability mechanism. Look at this example. A rectangular opening is created in a fractured rock mass with vertical and horizontal discontinuities. 6 blocks, number 1 to 6, could possibly fall if it were not for the confining effect of the horizontal stress. This is like holding books together in this manner. If we apply a confining effect, we can hold all the books. If we release the confinement, the books fall. This happens underground if the horizontal pressure drops, which can occur if the pillar progressively deforms. As a result, the joints have opened, unconfining the blocks highlighted in yellow and releasing them, in a similar manner to what happened with the books. So the blocks are initially stable, but can fall after some time, and all the blocks across the span could possibly fall. Block instabilities can to some extent be avoided or mitigated. For example, a rock engineering project can be developed with an awareness of the rock discontinuity orientation in order to limit the possibility to create unstable blocks. See, for example, this figure, where the slope has been cut parallel to the joint orientation. This eliminates the risk of a sliding block. However, it may lead to very flat slopes, which is not always possible due to space constraint. It can also lead to very steep slopes, where other types of instabilities, not covered in this module, can be triggered. Then mitigation measures are possible, among which active solutions, where the blocks are prevented from detaching from a slope, or passive measures, where a block can detach, but the fall is controlled and the blocks are stopped before any damaging impact. The choice of measures, active or passive, can be limited for certain applications, typically underground. Here you can see a sketch of active protection consisting of rock bolts placed in the slope and holding the blocks together, preventing the fall. Rock bolts are typically used with a mesh, as per this figure, where bolts and mesh are used to stabilize the roof. Passive solutions are more common on slopes where blocks can detach and fall, but be stopped at the bottom of the slope by properly engineered barrier. Examples of these type of barriers will be given in Module 3. These examples highlight the fact that discontinuity orientation is crucial when it comes to rock engineering projects. A large proportion of block instabilities can be predicted and avoided if the discontinuity orientation are properly surveyed and accounted for.